don't know Howard Rush. Howard Rush is a charter member of the Jive Combat Team, and now as a Lone Ranger, he rides throughout
Lone Jiver.
Lone Jiver, excuse me. Bass Reeves, what's the inspiration of the Lone Ranger, anyways. Howard Rush is now a Lone Jiver. He rides throughout the West on his white steed, wearing his N95 mask, doing good deeds, and handing out silver vortex generators.
Yes, thank you, Charles.
You're welcome.
The introduction, which was accurate except for the good deeds, I think. And okay, we'll talk about stunt plane control geometry and a program I wrote to cipher it. And let me attempt to share the screen. And where to go? I practiced this for a while and found out that I don't know how to do this. So there, look at that. This looks like the one. Okay, see that stunt plane control geometry?
Yes.
Okay, yeah. Kinematics. I'm not sure what kinematics is, but I think that's what this does. It's parts moving around. Is that right, Dave? Well, you can't talk because you're muted, but I see you nodding. Thank you. So yeah, I was reluctant to call it kinematics, not knowing what it is. And yeah, I'll talk about the program and also just the consequences of control system geometry in general. And even if you don't have the program, there'll be some tidbits that might be useful to you, but have something else to do. You sand something while I'm talking and you might hear something useful, maybe not, but you get something sanded. Okay. What it is, the program is an Excel spreadsheet with VBA macros, Visual Basic for Applications. It's a thing that comes with Excel, lets you write little programs and tack them onto the spreadsheet. Everybody has Excel, so it's kind of handy to hose around. Well, I guess everybody does. Everybody at work had it. And so I used it a lot at work because it's accessible to everybody. This program works with real Excel. It might not work with some Excel imitators because they might not have VBA. I don't know whether it works with all Excel versions or not. Mark Weiss wrote in a while back and said, I can't get your program to run. I blew him off, but it turns out, yeah, it really didn't run with modern versions. But I fixed it and it might now. But heck, it's free and you get what you pay for. So anyhow, if you have this thing and if you don't, let me know and I'll email it to you. If it doesn't work, let me know and I probably won't do anything, but it's worth a try. It does a 3D analysis of stunt plane control systems. It's a 3D problem because Bellcranks in one plane and the other stuff, the control horns are in another plane, and folks have attempted to do it on a sheet of paper and it really doesn't work. I've only done it for airplanes with flaps, and I really should extend that to elevator only airplanes because it's probably worth doing. I've had some combat planes that didn't work, and this might explain why. And it works for normal stunt planes. I've got a version built into it that works for airplanes with the Igor logarithmic system. And that's what I have in my airplanes. Let's see. What it's good for. Uh, there's my microphone. I'm self-muting. Relationship between control line motion and control surface motion. So you can see if your control system's linear and symmetrical. If it's not, you can fiddle with the input parameters to improve linearity or symmetry. And it can show you the mechanical advantage your system has over control surface aerodynamic hinge moment. It takes a torque to deflect the flap into the wind. Elevator, not so much, because the elevators kind of go in the same direction as the wind, and it's little. But deflecting the flaps requires pretty big torque on the flaps. And this torque we call control surface hinge moment. So you stunt people think of moments as a distance, but in general, engineering talk, a moment is a torque. And there's a spring between your handle and the airplane, namely the control lines. They bow back in the wind, and they also have elasticity. And so you're controlling your airplane on the other end of this spring and trying to bend the flaps into the airstream. And I think that you want to minimize the difference between the force in each line to minimize the spring effect. And therefore, you want to maximize the amount of lead out travel per unit of flap deflection. I put in a wrench analogy there. Force times the distance on it. If you get a long handled wrench, it doesn't take as much force as a short handled wrench. And you technical people see the units don't really come out right, but this distance, I'm pointing to it. You can't see me pointing to it. That distance is the radius out to the handle of the wrench times the radians through which the wrench rotates. Now it comes out right? Okay, so I think I think the hinge moment thing is important, and having leverage over it is important. And how to use the program. It says, behold the definitions and assumptions. Now, at this point, I have to switch programs, and we've been practicing this, and I'll see if I can do that. When you open the program, it comes up on this definitions and assumptions page. And you look at that to see what I call zero and which way is positive, and like sideways is positive out the right wing and stuff like that. And the assumptions, like, doesn't work for self-centering Bellcranks and a lot of stuff. So check that out. And then now back to, we'll return to the program shortly. Okay. Behold the variable names and signs on the PDF picture. Along with the program, I throw in a couple pictures that have the names of the variables on them and look like this, which you can't see here. And the variable names are kind of funny, but what they are is the names I use in the VBA program. And this uses standard airplane sign conventions, which I don't know whether you know or not. But the sign conventions are on here. Let me call to your attention the Bellcrank cartoon. There's one parameter here that turns out to have a big effect on the control system symmetry and linearity. And it's this guy right here, from the perpendicular to the axis of the bell crank. And I'll show you more about this later. But when you're messing with this yourself, be sure to fiddle with this dimension. Try stuff out because it has a big effect often. Okay. Now it says, go to the input sheet, your values. Now we're supposed to show the input sheet. It's supposed to show the input sheet. Here is the input sheet where you put the stuff. And you see that? See the yellow stripe there?
Yes.
Yeah, good. And let me point out the sign convention thing. Heed the sign conventions. By standard airplane signs, distances out the left wing are negative. So the distance to the left wingtip where the lead out guides are is a negative number. Well, when I put in nobler numbers as an example, this is a nobler, and forgot that to make this negative, and I spent much of last Saturday trying to get this thing working because I forgot to put in a negative number. Likewise, the elevator, zero in the fore and aft direction is I've defined as where the flap control horn axis is, the crack between the wing and the flaps. And so the elevator's aft of that, and in our sign convention, the X is forward. So that's a negative number. And I've mistakenly made a canard before by entering a positive number there. I should have a warning that pops up when you enter positive numbers for these things. It ought to be negative, but I don't. So just be aware. Some things are kind of weird. Now, we'll talk about the design process, what I think the design process ought to be. And I'll have to go back to, so that was a pretty fast transition, all of the design process. First, pick a maximum flap deflection. Don't pick any more than you need because you'll be sacrificing leverage over the system. Can you see that now, Charles? Pick maximum flap deflection. Good.
Yes.
As sometimes I see things here and I'm the only one seeing them. The default is 30 degrees, and I've always used 30 degrees because I don't know what the maximum flap deflection ought to be. And I don't know if the program works for anything else. It probably does. I suspect that we don't use any more than 20 degrees. I got instrumentation on my airplane, but I haven't recorded it yet. So I'll find out how much my airplane takes and then report that, but it might be different from yours. We put a camera on one of Paul's airplanes once and watched its flaps, but it wasn't calibrated, or looking back on the fuselage, it's hard to tell how much the flaps move, and we didn't put any marks on it. I should have taken a Sharpie and put a mark on there at 30 degrees or something. Well, he wasn't looking. Next, pick a handy flap control horn size. And what are we doing nowadays? About 1.5 inches. Yeah, use that. It's an independent variable, flap control horn size. Well, the way I do it, it is. And a good starting point is to have the bell crank be perpendicular to the lead out average when the controls are in neutral. And that's a good starting point. But when you iterate on it and fiddle with the parameters, it tends to work out that way. It's the best location. And a couple of people who I can see here, I won't name very many names, have attempted to, and maybe successfully, adjusted the push rod between the bell crank and the flap control horn to fix some issue with control symmetry. And what this does is just to rotate the bell crank relative to the direction the lead outs go out. And in these cases, I think they might have been ARFs, and they, who knows what it was beforehand, so they might have come out to someplace closer to perpendicular than they started. But it's hard to fix an airplane after it's built. Use as much bell crank travel as you can get, I think, without making the system too perverted. When you go through this iteration, I start with a lot of bell crank travel and go from there. And to set the amount of bell crank travel, you change the ratio of bell crank pushrod arm radius to flap control horn radius. And if you start with flap control horn radius by starting with a given flap control horn, you make the distance from the bell crank pivot to the output hole smaller. That increases the bell crank travel. And after you pick a bell crank travel initially, then the next thing you do is fiddle with the other parameters to make the flap deflection versus lead out travel a straight line and symmetrical, and use as much lead out in one direction as the other. And then look at the mechanical advantage sheet and try to make that symmetrical, mechanical advantage versus lead out travel. I'll show you the pictures here in a little bit. Let's see. Then after that's done, linearize the flap to elevator. And I'll go ahead and talk about that now because it's here. It's easy because it's all in one plane. Typically, it's not too far off usually from a plane, the control horns and the push rod. So you put the control surfaces in neutral and run the push rod between the control horns, make the control horn axis and the, not axis, but the uprights perpendicular to the push rod, and you're in business. Okay. Now back to the Nobler. So here's the input sheet to the Nobler. And once you've put in the numbers, the initial numbers, you push that button and it will lead you to this chart. there. And this shows the green line here is the most important thing. It's the flap position relative to lead out travel. This x-axis is lead out travel, and the other things are elevator and bell crank. This shows that the Nobler on the plans that George sent to Top Flight, which I got via Bob Emmett. The bell crank moves almost as far as it can. It's so it has quite a bit of leverage over the controls, but the shape is awful. And I'll notice that it takes, let's see, is this up or down? Aft lead out is up, I guess. 2.5 inches to get to full up, and 3.2 inches to get to full down. So might be more effective at the top of the hourglass than it is doing triangles. Might not be able to do triangles too accurately. Now, the slope of this curve, and I've fared a line through it. Excel will do that for you. This trend line tells you the slope. This slope is 1 over mechanical advantage. Mechanical advantage is the derivative of this flaps versus lead out travel slope. And it's maybe a more useful thing to look at when you're fiddling with the inputs to try to get things symmetrical. And this is the Nobler as it comes, and mechanical advantage goes from like 8, one side, 8, let's see, what is that, degrees per inch, to more than 15 at full up. So that's kind of crummy. Oh, yeah, this is an aside that elevator versus flap on the original Nobler is 1-to-1. You can't see it. Now you can.
Yeah, you can.
And yeah, I've heard rumors that it was not 1-to-1, but it is on George's drawing. Okay. Now, here's the tricky part. Well, I guess I can get there this way. I changed these items, these in the gray cells. You see them, Charles?
Yes.
See the gray cells. And there's the famous push rod arm rotation on the bell crank. And go into this chart, see, I was able to move the bell crank even more. It's almost plus or minus 90 degrees. It goes to 100 here because it's askew a little bit. It doesn't go through 0. Because lead outs go back from it, I guess. And this line's nice and straight. And mechanical advantage, isn't that pretty? It's all symmetrical now. Less than it was. And so that was pretty cool. Now, let's see. I went the mechanical advantage improved by 6%, but I tacked on a 5-inch or a 4-inch bell crank just to see what would happen, and got 41% in improvement in mechanical advantage, and it didn't deteriorate the shape in or much. Now, here's you see a couple of bell cranks there, Charles?
Yes.
Yeah, amen. these are the changes I made. I moved the bell crank forward. Red is the new one, and rotated it so it's perpendicular to the lead outs. And here's the output hole is askew 7.6 degrees, wasn't it? Something like that.
Yeah, 7.6.
And I moved the flap control horn forward. That's where it came out. And I've been telling people that you can optimize this with the flap board either straight up and down or forward, and it doesn't matter. But in this case, it did. And tentatively, John Miller is right and I'm wrong about the tilt of the flap control horn. So I won't admit to being wrong quite yet, but I'm pretty sure that he's right and I'm wrong. The bell crank on it, or control horn on it, flap control horn on it, tilt forward. Now, our Jive Combat Team Archives also has plans to the Snaggletooth 2 Mustang from Al Raby. And I shall attempt to find that. Now, see the input sheet, Charles?
Yes.
Amen. Okay. And behold that this starts out with the output from the bell crank on the left side of the bell crank. This is the famous reversed bell crank. And looking at the what these numbers give you, this is the stock Snaggletooth 2. The flaps versus lead outs line is, so the slope is negative because of that reversed bell crank. The reversed bell crank doesn't have any effect on the kinematics, but does on some gyroscopic stuff maybe. But the striking thing about this, I think, was that bell crank doesn't move very far. It only goes like 26, 27 degrees in either direction. And mechanical advantage, this is the flaps here, that's elevator, which I'm not too excited about. Mechanical advantage is nice and symmetrical, but it's not very advantageous. This is 1 over mechanical advantage. 15 is pretty big. So now, according to my notes, we go back to the other thing. Here's the first change I made to the Mustang was I tried to get more mechanical advantage without messing up the symmetry, and I couldn't do it. So I gave up and put in a 5-inch bell crank. And just putting in a 5-inch bell crank and offsetting that hole came up with a pretty good control system and more mechanical advantage. It was symmetrical. Then I got greedy and tried to get even more and reduce that distance farther, and I had to tweak the flap control horn a little bit. And came out with something that wasn't quite as pretty, but got more mechanical advantage. Now I'll show you the plots. See the 3 curves there?
Yes.
Hey, good. And this was the original flaps versus lead out travel. Lead outs don't go very far, less than 2 inches in either direction. And it's kind of symmetrical, but they don't have much mechanical advantage. The first change gave a pretty nice curve, got a lot more lead out travel, a whole lot more mechanical advantage, 188% of the original. And then another try. Second picture I showed is 242% of the mechanical advantage of the original. So I'd stop here, I think. But you know, how much mechanical advantage do you need? uh, uh, it depends on the hinge moment, and it's hard to tell what it is analytically. So I just put in a lot in my airplane. I have even more than this, I think, especially full flap deflection. And I also plotted this versus flap deflection, which is maybe more useful. There's the three curves. Now, that's it for the Mustang example. I have a conclusion or two, and there's a conclusion. See that?
Yes. Yes.
You can't fix airplane control problems with the handle. There's nothing you can do. Because the spring is between the handle and the airplane. So to gotta do it in the airplane. And I have an asterisk here because Larry Ringer has some interesting control handles. There's probably other ways you can do it. If you make a control handle like Orestes is, which is a strap going around a handle, you can tailor the control spacing versus handle deflection with that. And that might do something useful. The line spacing at the handle is a dependent variable. And so once you get the airplane how it's going to be, you just got to pick the line spacing at the handle that makes it work. And if you have a lot of leverage over the controls, you got a big handle spacing. The next item is that control horn heights are arbitrary. I think I've said that already. I took the Nobler for the heck of it and doubled the size of the control horns and doubled the distance from the bell crank pivot to the output. And it did not change the mechanical advantage. But it's a useful thing to do to have tall control horns because it reduces the effective slop in the controls, particularly now that ball links are falling out of favor. The Nobler plans were pretty cool. In the old days, remember, people used music wire for push rods, and it tended to flex. And with half-inch control horns, it was probably a significant problem. And on the Nobler plans, the Bellcranks showed little bitty holes in each bulkhead. So the push rod going from the flap control arm to the elevator control arm went through all these little bitty holes to keep it from flexing. Third item here, so I think I said, you don't care what the bell crank does. So plotting stuff versus bell crank motion is kind of a waste of time. What you care about is the relationship between the lead out travel and the control surface travel. And yeah, I mentioned that yeah, I've got another program I'm working on that can tell you when you have enough mechanical advantage, but you got to know the hinge moment to tell whether you got enough mechanical advantage. And as Gary Letzinger, a local wise person, said, hinge moment calculations are easy to do, but hard to believe. So you're going to have to measure it in a wind tunnel. You got a wind tunnel. Frank Williams could do it. Or by instrumenting the lines. If anybody wants to do that, we'll talk. Putting strain gauges or something on the lines and taking recordings. That's enough. So go ahead and see if anybody has any questions, if anybody's still here. Yeah, I see a couple guys here.
Yeah, any questions? Go ahead and raise your hand digitally, and I'll go ahead and unmute you. I know Peter had a question. Peter, let me do Peter Kolosky. He had a first one, a question. Go ahead, Peter, unmute yourself.
Yeah, the idea that the bell crank isn't in the forward and aft plane, that the rear of the bell crank is lifted. I hadn't seen that, but I'm guessing it's common.
Well, I did it on combat planes. And you can do it to avoid obstacles in the wing, like the landing gear mounts and stuff. Although that didn't be in the other direction. I haven't found that it does much, which I guess is good if you have to do it for some reason, but doesn't help or hinder one way or the other. I on previous airplanes, I found that the sideways location of the bell crank was a big influence, but on the Nobler and the Mustang, it didn't seem to matter. Dave, I see Dave. Charles,
Dave, which Dave?
Dave Hall is.
Oh, there we go. All right, go ahead, Dave. You're still muted. There we go.
I think that would be a tangent effect. So it's going to be pretty small if you're inside the narrow depth of the wing and you've shifted the bell crank only slightly up.
I think he was talking about tilting it.
Oh, tilting from the plan view, having the output arm, let's say your notional 7-degree shift.
No, the other about the y-axis, rotating about the span.
Yeah, line attachment point aft high.
I got a picture I could show you, but I'd have to share it.
I don't understand the description when you say aft high.
Let me find the picture.
High to me is z-axis.
I'm high, all right, but not on false drugs.
Yeah.
And I am recalling that the Nemesis had that, where the back part of the bell crank was higher.
Yeah, and that was
the push rod.
Yeah, that was to make the push rod, which was a piece of music wire, straight, which was kind of a breakthrough at the time.
I think you're still looking at a tangent of a small angle kind of problem, though. So I don't expect you'd see a lot of influence.
Yeah, here's the deal. The tilted bell, you can see there.
Now I understand.
Yeah. Okay.
I have a question from the chat box by Bruh832. How do aerodynamics and control surface geometry and stunt plane design collaborate for precision maneuvers? And how does pilot skill influence optimal performance?
Oh, that's easy.
Yeah.
I'm sorry. I I couldn't even remember that whole question, let alone.
Okay. The first part was how do aerodynamics and control surface geometry in stunt plane design collaborate for precise maneuvers?
Oh. My mind is blank. I'm sorry. I think that this leverage that I talked about helps precise maneuvers, but that's not the collaboration of aerodynamics. It helps to have a linear lift curve slope, I think. Helps not to have hysteresis in the lift curve slope of the wing. Where's Paul? Ask Paul.
Let me unmute Paul here.
Yeah, unmute Paul.
Okay, I'll unmute. I don't know that it's as simple as
Yeah.
some people would like to think it is.
Yeah, right.
There's a definite correlation between flap areas, elevator areas, stab to elevator ratios, ratio of the flap area to the wing area, center of gravity, speed you're flying, mechanical advantage, all of that plays into it. It's hard to separate all those.
And if you go to flyinglines.org, in the stunt section, there's how to trim your stunt plane. And a lot of it's there. But yeah, that's a tough question.
Can I make one comment? Is on Howard's presentation, it's very good. To me, the most important step is to get your sign convention right. If it is not right and you go build that into your airplane, you have maybe make a big mistake.
Building it in the airplane. No,
you've got to be really sure your sign convention is correct.
I have a question from Doug Moon for you, Howard. Can you go over the let's see here. Can you go over the input page one more time, please?
I call it up and talk about it, I guess. Let's see. A good one would be that Nobler after it's fixed, because it had yeah, here we go. Oh, did that work?
Yes, it did.
I double clicked on it and it started working, which seemed to be too easy. Okay. Now you see the yellow and gray stuff?
Yes.
Okay. These are the inputs available to you. Oh, you can, if you have an Igor system, you press this button and it switches to the inputs for the Igor system. Yeah, can we get it back? Yeah, toggle back. Yeah, here's conventional control system. I could go through each one.
Please.
Okay. Distance forward of the flap hinge, which we assume is straight, or the flap control horn if it ain't, of the forward lead out, distance forward of the crack of the aft lead out, distance of the lead out guides, the average lead out guides span wise, like from the center of the airplane to the left wing tip. Distance of the bell crank forward of the crack, and that's something that the crack, namely the flap control horn, where the hinge line between the flaps and elevator, or the flaps and wing. Yeah, that had an effect on the Nobler. I haven't noticed it on other airplanes. you'd think that once you get this control system, you just plunk it down in any airplane. And I don't know why you can't. Once you get it figured out, that's sort of a mystery. This is the distance the Bellcrank axis is to the right of the airplane center line. It didn't have, I fiddled with that. I couldn't see that it had much effect. Bellcrank pitch, the distance that the platform was tilted, that Peter was talking about. I tried changing that, didn't do anything. Bellcrank lead out arm radius, half the Bellcrank size, 1.5 inches for a 3-inch Bellcrank. That has an effect. And Bellcrank size is an interesting thing. You can get this leverage from either Bellcrank diameter or lead out or Bellcrank rotation. And so you can draw a picture of your wing and try different size Bellcranks, and for a given rotation times diameter, see what size Bellcrank does the least damage to your wing. As if you consider all the lead out positions and 90 degrees of Bellcrank rotation, that uses up quite a swath of the wing. It keeps you from having an adequate shear web in the left wing. So yeah, you can trade Bellcrank size for travel. Bellcrank pushrod arm radius. This is the distance from the Bellcrank axle to the hole. And this is the one that you fiddle with to change the total Bellcrank rotation. Height of the Bellcrank pushrod arm. This, Dave, does seem to make some difference. And although I assume that the Bellcrank is on the center line, one could have a ball link and claptrap to mount it that sticks up. And this Bellcrank lead out arm rotation, 0 flap deflection. This is this is the angle the lead outs go back from the Bellcrank axle to the lead out guide typically. Well, it's perpendicular to that. Well, that's where you start from. It's the angle that the Bellcrank's at when the controls are zeroed. And this is the weird Bellcrank output arm rotation, pushrod arm rotation from the perpendicular to the Bellcrank axis that does so much. You fiddle with that, you'll enjoy the effect. You know, I've been thinking about just wrapping some loops around this and having it automatically iterate and sit there for hours and come up with a really cool control system. But I kind of don't know what to have it look for. What's the optimal? What's the performance index? Flap control horn radius, 1/2 inch and a nobler. And the flap control horn arm rotation at neutral. That's the one that John Miller tell you ought to be perpendicular to the push rod. And maybe so. What is this? Oh, this is the aft push rod, the one going to the elevator from the flap. Looks, yeah, rotation of the aft push rod, aft control horn. Sideways location of the push rod arms. This is noticeable if you got ball links on there that are off the center line. The what stunt people call the tail moment, the distance between the hinge lines. How far the elevator axis is above the wing center line. Actually, how far it is below the wing center line, because there again, there's a funny sign. The z-axis is down in airplanes, so if an elevator is above the wing, it's stabilizers above the wing. This number is negative. Elevator push rod arm radius. This is how much the elevator control horns rotated at 0 elevator angle. You have to look at the cartoon to see what that definition is. How far offset from the center line the elevator push rod attach point to the control horn is. And here's one. Elevator deflection from the at 0 flap deflection. And this works out to about 4.5 degrees with an impact, typically. And other airplanes can be 0 if the stabilizer's leading edge is up a little bit, might come out with 0 or something close. Either stabilizer would have some positive incidence there. The elevator would be down a little, maybe because of the flow over the wing coming downhill toward the back of the airplane. If the tail's up a little, it would have a negative angle of attack. And then Brett says that because the airplane is flying around in a circle and the prop is rotating, there's this gyroscopic moment that requires down elevator to counter. So I think that if you build a stunt plane and find if you get the control system symmetrical and you find that it turns tighter one direction than the other, that's the thing to vary. You shorten the aft push rod rather than messing with the symmetry of the lead outs to flap. And then maximum flap deflection, which is 30 degrees. You can try other stuff. In fact, if you know that it doesn't take that much, you ought to put in less. I think it might work. Never tried. I don't. So there, I ran through that. Does that answer your question?
I think so.
Okay.
I have another question here in the chat box. Is there such thing as Crafton? In fact, that's my question. Is that a real thing, Howard?
What?
Crafton effect, Kraton.
Never heard of it.
Never,
Isn't that those little abrasive wheels?
I don't know. I won't ask the question. I'll skip that guy. The next question is from Sandpiper.
I don't remember.
4-inch bell crank optimal or of? Excuse me. Let me start over. Is the 4-inch bell crank optimal of? Would a? I think he's asking, would a 5-inch bell crank be better, or do we use the 4 just because that's what's available?
Ha ha. Well, 5 would give you more leverage. Wouldn't have to move as far for the same leverage. But there's a structural problem with it. It'd have to be stronger. But the main problem I see is the lead outs go around a sharper angle at the wingtip. And then you've got a situation like with a cable handle where there's this springy thing with the lead outs going around a sharp corner and maybe some drag on the controls, and that's not too cool. So that'd be a disadvantage of one. What do you think, Paul?
Oh, Paul, you got to unmute yourself, Paul. I'm sorry, Paul. Try it again.
He's speechless.
Try it again, Paul. Sorry. My
Okay, there we
there
go.
it goes.
Now, the question, I'm trying to remember now, just like
Is 5-inch bell crank worth doing? I think is
the larger bell crank worth doing. Yeah, like you say, if you go to a larger bell crank, you're also squeezing it down at the lead outs and then expanding it back out at the handle. Is there more friction at the lead outs because of that? Maybe. How significant is that? I don't know. I don't know what the coefficient of friction is between those lead outs and your little guides and what they are, etc. But you got to get around all the structure in there too. And the wing spar is a problem. And if you got landing gear in the wing, you got structure in there for the landing gear. And so this is always the battle I face. I'm a structures guy. I put the structure in first, and then I try to put the bell crank in. I hate kinks and stuff in my primary load path. So,
yeah.
But sometimes you have to. But yeah, it's a battle if you swing that lead out around more. I guess if you made a 6-inch bell crank, you might run into some of the structure for your landing gear, and it's going to come back, and whether it's going to clear the spar depends on how far you move it, I guess.
Yeah, wouldn't have to move as far.
Well, your put is always to move the bell crank as much as possible.
Well, yeah, if you want to move
Well,
it.
yeah, come on. Just say yes, you got it.
That was hyperbole there.
So
for a given mechanical advantage, it's pretty much the angle that the bell crank rotates times the diameter of the bell crank. So you could rotate a 4-inch bell crank all the way or a 5-inch bell crank less. I have
a new one I'm thinking of building, and I'm considering a 5-inch bell crank on it. And we'll have to see how that works out. I don't know. Your program is really cool because it can solve numerous problems, and I've had a couple of odd problems over the years, and the P47, the first P47 was one of those, because I've got the WFA in it. And when I went to the P47, I got to back up. The P47's got a big fuselage in it, the flap. And so when I put the WFA in it, I said, aha, I'm going to be smart this time. I'm going to put it on the inboard side so that when I turn the screw, that's the way the airplane is going to go when I turn the screw. Well, that moved all of the stuff way inboard, and so your push rod and Y on your flap, to the elevator and the bell crank were way off center, and so I had to counter that by moving the bell crank, and that was really cool because you could just move the bell crank and you could see the impact that it had on the entire control system when you did that, and so it's funny, but it ended up being farther outboard. It's a reverse bell crank, of course, but it went farther outboard to get linearity in the system. So without that, I would have probably not put it as far outboard. I'd have put it more inboard, but it would have not have been linear if I had not paid attention to that. So that was very interesting, and so yeah, it does really good things. You just have to pay attention to the sign convention. You'll do something and just like, well, that doesn't make any sense. Why did it do that? Well, when you get it in backwards, it'll do that.
Yeah, I better put in some warnings there. Oh, and thanks, Brandon, for the thing about Kratom. As I said, I'm high, but not on false drugs. Carry on. So, excuse me, Paul.
No problem. I'm done.
Any more questions?
Oh, I did have one more question. All right. So your starting input is put the bell crank perpendicular to the lines as they go out to the inboard tip.
Yeah.
That assumes at the beginning, then you know exactly
where they are.
The dots are going to be.
Well, if you build the same airplane over and over, you get a kind of a clue. But
you build
actually,
the same airplane.
What you do is you call Paul Walker and ask him, where is the fashionable lead out position this week?
This week, just this week? How about this day? What? Yeah, because you can move them quite a bit. If you move them an inch, that's going to change that angle.
Yeah, fortunately, it doesn't have much effect.
It doesn't have that much effect.
I don't think
okay.
So.
All right. I haven't run those numbers, so but I'll do that and satisfy myself.
Doug has a good question. How do you build all those angles perfectly on the plane? I think that'll be tough. After looking at these pictures and looking at the tiny differences in the location of like the hole in the bell crank, send cut send. I'm going to get them to make parts because these are the guys, and there's other people like them. I think now you send them a CAD drawing of like your bell crank or the carbon in your control handle, and a couple days later you get back this really accurate piece of stuff. So that's my plan for the future.
Go ahead, Jonathan Carrata has the question.
Oh, it's first of all, I was going to say that's a great piece of work you've done there. Absolutely fantastic. And I think a number of the questions that have come up and discussion points that have come up, there are so many moving parts and variables still to be answered. As you know, I mucked around with something a few months back, and it's an analog, if you like. And a lot of these variables you can mess with on my model here. You can sort of put the input, you can change the length of your push rods, you can set your flaps, you can work out your horn dimensions and so on and so forth. You can look at the effects of different size cranks, bell cranks. The issue of is the 5-inch better than the 4-inch, all that stuff. Another bit, an extension to this would be to take this down, obviously, to an output, so that you could measure you could measure the differences here linearly. But to me, I like to find the quickest way to the beach, and I had these questions in my head before.
You might get lost on the way to the beach if you don't rotate the.
Beg your pardon?
You might get lost on the way to the beach if you don't rotate those control horns 90 degrees.
Yeah. Well, the quickest way to the beach for me is to try and work out a way of getting an answer. And if I can't, I try and work out a way of getting it.
No.
And to me, this is just a very, very simplistic Heath Robinson hands-on. And I've used it on a couple of aircraft so far, and it works absolutely beaut, because you can calculate what you want, 25 degrees, 35 degrees, whatever you like, fit it into the structure of the aircraft, mess around with the push rod lengths and so on and so forth. And if you do your measurements correctly, you pop it all in and it just works spot on. But the issue of loading on the elevators and flaps and things, that's another story.
That's another story.
And that all comes into it too. It's a fascinating piece of work. It's what makes it all very interesting, doesn't it?
Thank you. Another question that Tim was going to ask, but I told him not to because it was too embarrassing, is I think he's going to ask this. Little airplanes have to have smaller bell cranks than big airplanes, or is it the other way around? I don't know.
I muted you, Tim, if you want to respond, Tim. You got to unmute yourself, Tim.
That was the question. I don't have the response. Now it sounds like 5 inches. We're going the other way.
On a junior flight streak, what size bell crank should you use? Well, it doesn't have flaps. So. Never mind. There was a guy in this neighborhood who built half A's with 5-inch bell cranks and flew them on 70-foot lines. Paul doesn't like to think about it. Didn't he fly his first flight on 70-foot lines, his second flight on 25-foot lines, just to bracket allowable.
But he had that little half A plane, and the bell crank was like 80% of the chord of the wing. It was huge, and but it flew okay.
I'll go ahead. Let me get you, Dave Hall, just a second. There you go, Dave.
Yeah, that was the guy that had the pseudo combat half A's. I'm forgetting his name right now, but the plane was called Ridiculous.
Rich Porter.
Rich Porter.
Rich Porter. Yeah. So if you wanted to go look that up, I believe the articles are searchable in the AMA archives. To the question, if I can, Charles, to the question that was asked, a really, really broad question about aerodynamics and controls in stunt planes, start talking. I think probably one thing to do is recognize that there are different branches to the tree. So if you start down the path of optimizing one way, and let's say you're doing it, and this would be the danger, in my view, Howard, of finding an optimizer like they might use for stress problems. You start down a path and you say, well, I'm kind of married to 3-inch wide flaps at the root. And so I have this force problem at the flap bell crank. And so I need these other things. And depending on which parameters you pick first, you end up driving to converge to a local maxima at that point, which is maybe a different place that you end up with. So I know a lot of the discussions that you'll hear on Stunt Hanger, you go look at them, you'll see let's say a pattern master or / East Coast kind of view of very large flaps and all the optimization that has to go with that in order to get a flyable plane. Whereas you go to a different school of thought where their branch of the tree, the solution set, angled off in a different direction, and they will say, don't put those giant flaps on there because we want to manage the forces better, because then we can do this with the bell crank, and so you end up in a different place. Neither one per se is wrong, but you might end up with one guy flying it with a certain size handle, another guy needing a handle that's twice as big. It's just it's how you optimize it. So it's a difficult. There is not one answer here for this universal control system, obviously, but
Thank you very much, Dave. I want to just encourage everybody to hit the like button, please. Smash the like button. We're kind of light on the likes, believe it or not, even though I think we've had really good discussion.
Yeah, you gotta have a better speaker to get
Great.
that.
Where
We
is it?
have some super chats I want to acknowledge. Reagan Revita gave us I think $10. Thank you very much. Appreciate that. Then we have another super chat by Shane Murray for $4.99. And the comment was, Howard, you saved my life. Howard, you are a lifesaver, just so you know.
Oh,
And then Bill Typhoon, he gave us $2, I think. It shows $1.99. And thank you very much. I actually gave you timeout, Bill. I'm sorry about that. I have a lot of trolls tonight. I was busy trying to figure out what's going on. So I inadvertently, the guy gave me a super chat. I apologize. I actually timed you out for 24 hours. So
oh dear.
sorry about that. I think I'm all caught up on the chat box as far as super chats. So we got 3 super chats tonight. Thank you very much. And now we're up to 25 likes. Thank you very much. We have some noise. Whose background is loud? I hear. All right. Anyways, any more questions? Any more comments? Any more?
Peter has a question.
Go ahead, Tim. You said Peter's a question?
Peter has a question.
Okay.
Yeah, Howard, what was the impetus? What made you even start this program? And when? How long ago did it begin?
Not tonight's program, but well, I think it's when Dave Gardner was do some cartoons about a upright flap horn versus a leaning forward flap horn, and started ciphering based on that, I think.
What year?
Oh, I don't know. It was probably 10 years ago.
And then Peter, you had a question, Peter? I'm sorry. I mute you, Peter.
Okay, thanks. Yeah, my questions are really general. I was saving them for the end. They're kind of like after party questions, really. This seems like a really great program, and it's very mathematically oriented to do calculations. I wonder if there's been a consideration, considering that sometimes people put in the inputs backwards, negative Z or positive Z here and there. Any thought to making a graphical representation of the inputs so that a person can see, that they've put in bell crank pitch or that they've put in a different orientation?
That'd be great. I don't know how.
Yeah, right.
Well,
I'm not volunteering because it sounds like a big project.
Yeah, there exist, I think, kinematics programs. I looked into that, and either I didn't understand them, or they were expensive, or there's something off-putting about them.
Okay, another question.
That'd be cool.
So, we're talking about instrumentation, and we're talking about generally trying to achieve symmetry, etc. Of course, one of the things we love about control line is its lines, a handle, a bell crank, push rods. Every year is 1952, I sometimes say, because so much development happened in the 1948 to 1952 era in, engines and control line technology, Plymouth Internets and all that. Has anyone considered electronic instrumentation and control systems for control line airplanes?
Yes, instrumentation. Some of us have done that. And as Doug says, Kim Doherty made a fly-by-wire control line airplane. And those of us who are flight controls engineers, I think me and Brett and Igor jumped on that and tried to get rules passed against it, because when you do that, you will have just made it an autopilot contest. Because you can't tell what automatic stuff is in a electronic control system once it's electronic.
Yeah, it'd be a totally different sport. And this question is this question is very basic, I'm sure, to many. But what is the? I'm seeing how the Igor system operates, the effect of it, which is that there's more flap deflection near neutral and less near the end. And what is the benefit of that in flight?
Paul is grinning there, and it's rightfully muted.
I'm sorry. Yeah, there's 23 of you guys. I'm trying to keep up with all of you.
Yes, Howard's going to point out that I've told him that if I'm building a AMA airplane, I wouldn't put it in, but if I'm building an FAI airplane, I certainly would put it in, and I still mostly feel that way. However, you might see me at the Nats this year with the nonlinear airplane again. What it does, to answer the question, is it gives you more flap deflection when you're doing round maneuvers versus a tight corner. When you do a tight corner, you don't get as much flap in it. So you can turn a tighter corner. So you get tighter corners and nice rounds at the same time. Whereas a system without that nonlinearity in it, you get the same no matter where you're at. And the plane I've been using for the last 5 years has got a really good corner, but I suffer in the rounds a little bit. I really have to pay attention in the rounds. And I think that's hurt me in the last 5 years. So I'm going to go back to the nonlinear thing more than likely.
I have some pictures of the mechanical advantage of both those systems, which are kind of interesting. I'll go keep talking, and I'll try to find those and bring them out.
All right. Hey Joe, on your iPad, can you raise your hand digitally or not? I don't know if you can or not. If you can, let me unmute you, Joe, or ask you to unmute yourself.
What can I do for you? I'm not smart enough to be in this conversation.
Oh, I thought you had a question, Joe. I just figured you did.
Oh, no, I don't have a question. I'm listening. I'm all ears.
All right. Wow. That's same way.
Howard made a comment earlier that we had put a camera on one of my airplanes and flew it. And I just hit the corners as hard as I could. And we wanted to see where the flaps would go. And we did get a video of that. We didn't put angle marks on the fuselage, but I looked at where the flap went down, and it went down, and there was a paint line that went right by it. So it went down to that paint line. I took it home and measured it, and it was 20 degrees. And I gave it everything it had. And it was an aft CG. It was everything you needed to do to make that flap go to 30 degrees. And it was 20 degrees. And so when you look at the Igor stuff, 20 degrees doesn't buy you much. So all the nonlinearity in the Igor stuff is between 20 and 30 degrees of flap motion. Buys you a couple percent, but not much more. So you really got to move the flaps to get that nonlinearity in there.
Here, I just shared the this is the airplane I'm flying now, and I should also call up the other impact, which I don't see. Shoot,
that's the new dog.
It's actually, well, they're the same theoretically, 5 and 6, and anyhow, this curve is concave up, and the other one's concave down. Is the upchuck of that. So yeah, I'm not doing a very good job of showing this.
You're doing good. We got a
Well,
like from Dennis Adamison. Thank you, Dennis. Appreciate that. And Dennis is a member of our YouTube channel. He's watching this, I guess, tonight.
huh. Yeah, let me stop this and I'll look for the
Okay.
airplane for the comparison. Okay. I got stuff on two computers, so it's a kind of a nuisance.
I understand. Yeah.
Charles, I've just had a thought. Paul, have you ever considered a system that might give you both linear and non-linear control? A
Fine.
dual system?
I don't know what you mean.
Well, you were saying that one gives you an advantage in the corners and the other gives you an advantage in the rounds.
That's the nonlinear Igor system.
Yeah. Would there be any advantage in designing a system that gave you linear and non-linear control of your flaps and elevators?
I think you go to the nonlinear because you think that's an advantage.
Okay.
It's like I said, I've used his program, looked at it till I was blue in the face, and between 0 and 20 degrees of flap, there's not a lot of nonlinearity. It's all from 20 to 30 degrees where you see the big difference. So
So what makes those big differences in performance are minute changes. They're very small increments at the in the control system.
mhm.
It's hard to believe. Yeah, it's all good fun.
Okay, let's see.
Doug Moon had a comment. He said that's what Igor's does.
That's what Igor does. What does that mean?
Gives you both linear and nonlinear.
No.
No, I can't. Can't do both. Not
Oh.
on one bell crank.
I've got both these things I can show you. Here is it's the standard impact, I think, isn't it? Yeah. Like it's around between 5 and 10, and it's concave down. And at maximum, the worst mechanical advantage is at maximum flap travel or maximum lead up travel, the extremes. And now let me go to this is with the Igor system. And this is another aspect of it. Not only the rotating the airplane easier in squares to make squares look good. It has a lot better mechanical advantage toward the maximum control.
Mm-hmm.
It's concave in the other direction. And what elevator versus flap looks like on this is.
There you go.
Yeah. Okay. There's something in the way of.
It's a little bias there.
Yeah. Let me. There it is.
See, at least out to 15 on that, it's fairly straight. And it starts to slowly move to 20, and then it really takes off.
Yeah. So
if you're just moving them plus or minus 20, you're getting a little bit, but it's not what it could be.
Yeah, and so
So I tried playing with setting the flap deflection up to 20 and seeing if I could force it to give me that non-linearity approaching 20, and I could never get it to work.
oh, now what Bill Werwich did long ago, and
Yep.
I think Chris Rudd reproduced more recently, was a cam following thing.
Yeah.
Hmm.
That was a funny thing. It had a push rod that went to the elevator, and then another push rod that went from the elevator back to the cam following thing, which drove the flaps.
You think there'd be an easier way to do that?
You'd think, yeah.
Okay.
Fascinating.
Just a second, David. Jim Vornholt, you can go ahead and unmute yourself, Jim. You had a question, Jim?
No, I just couldn't get it off. I couldn't get the unmuted off. I was
Yeah, I
wondering
know.
what was going on.
Yes, I know it's a little bit different format tonight. During Howard's presentation, we didn't want any interruptions, so I had everybody come in muted, and they couldn't unmute themselves
Yeah.
unless I
Okay.
gave permission. That's why it's a little different format.
Okay, I understand.
But you're not in the doghouse or anything. You're all right.
I thought I'd done something wrong or something. Yeah, well, thanks. I appreciate
You're
that.
welcome. You're welcome.
Yeah, I understand. Okay, thank you.
All right, go ahead, David. David Hall.
Yeah, a couple of comments. So I think for John's question earlier, it's not a single piece of hardware that dictates black or white that it's nonlinear or linear. If you looked at the charts that Howard was just showing over, let's say, a significantly useful range, you could do a linear curve fit and look at the R-squared value, and you're probably going to be in the 9.9s. And so to somebody with holding a handle, it's linear. But then you could see how, given the opportunity mechanically, you could fiddle with the corners of the envelope and the control envelope and start getting that nonlinearity. One thing that occurs to me right off is if you had let's call it a 3-piece bell crank, if you were willing to live with the complexity of an articulated bell crank where you flex it, you could start tuning with, let's say, for example, you had a cam on the end that had the lead out passing through it. And on the outside of that cam was simply the hole for the lead out. But on the inside of that cam, there was a gear. And you can run that gear like a planetary off of the bell crank platform. So there's ways to do it without, the previous conversation of running a push rod way back to the tail and then back to the front again and so on. But the question that, certainly my problem would be, I just need to stop hitting the ground. These other guys that are worried about, finessing it around the maneuvers, they might be able to see some advantage for tuning that. So potentially with a take apart airplane where you could get at that bell crank, you could change that gear ratio in there and you could fiddle with those cams. So that's, just something that occurred to me.
Oh, very good. John Miller, go ahead and unmute yourself, John Miller. John Miller, there you go. John Miller, you have a question, John? Can't hear you. I might have heard your chair, maybe. Hope you heard Howard. He paid you a compliment earlier this evening, John.
Tentatively.
Tentatively. He thinks you might be right about the flap horn need to be tilted toward the bell crank.
Yeah. Probably. Yeah.
All right. There was someone else who had a question. I lost place with them. Let me see here. Oh, John, you unmuted, John. Sean Miller, is maybe your bandwidth not working? I know you've had problems in the past.
There's Philip. Philip, don't go away. We'll talk later.
Well, we're talking now, Philip. Go ahead, Philip. Go ahead and mute yourself, Philip.
Well, we had a private issue.
Oh, okay. I know Philip has a question.
No, really, I don't. The stuff that I understand, I agree with. The stuff that I don't understand so far over my head, there's no sense asking the question about it.
Yeah, you're not alone in that.
I think I understood most of what he's saying, and it makes perfect sense. I've always wondered about Bellcranks forward and Bellcranks reversed, how much difference it really makes. And I built 2 airplanes identical and put one of them forward and one of them reverse. I'm not near the flyer Howard or Paul is. Never will be, because I'm having too many problems with my neck. Never would have been anyway to match those two. I watched them both and they're amazing. But I couldn't tell enough difference in it to say you need to go this way or you need to go that way. It's one day one seemed to fly better, and the other day another one seemed to fly a little better, but they're so darn close, I can't tell the difference.
Well, yeah, there's no difference in the kinematics, if we got that term right. But the gyroscopic thing could be a difference. Well, I've got a story to tell, but however, there's a neck issue, and you're comparing yourself to Paul. Paul has aftermarket parts in his neck. That's
whatever Paul's got, I've watched him a lot of time, him fly, and you and Paul and Aristides and Fitzgerald are just on another level.
Well, I don't know about Aristides and Fitzgerald, but we two are part titanium.
Oh, okay.
Anyhow, I built this one electric stunt plane, and I had a backwards prop on it and a normal bell crank, and is this the story? It worked okay, and so then I built the new airplane thinking I would have a backwards prop on it and put the Igor system in it, again with a normal bell crank, forgetting that the Igor system reversed the sign of the control. So now I had up in the front and down in the back. So this new airplane with the backwards prop at the top of the hourglass would do this Lomchevac.
Yeah.
And fortunately, it turned out that the forward props that we got from the Canadians and then Igor worked better anyhow. So
yeah, that was confusing to me when I first started with electric. One of the first things I did was try a reverse prop and a forward prop, and somebody's going to say which one's which, but okay, a conventional propeller against a propeller that turns the other way, guys. Anyway, I will admit the left-handed prop seemed to make, at first flying it, I thought the hourglass was much easier with a reverse prop. But if you fly it enough to get used to it, you realize that you're giving up a few points here and there on other maneuvers. So it just doesn't, it works out to where, okay, the hourglass is much better. I'll admit that. It's much better. That first turn, second turn, actually, in the hourglass is much better. But there are places where the reverse propeller will bite you if you're not real careful.
Yeah, the most interesting thing I found with it is switching from one to the other, and I had some matched pair of props that I put on one airplane. The swirly air, at least in flying speed, the swirly air effect is greater than the torque effect. So I had to tweak the flaps opposite the way you'd think you'd have to tweak them to compensate for torque.
Not only that, but then when you've built planes all your life that go along with Mr. Whiteley's things that always work. When you put that left-handed prop on there, they no longer work. So it's quite a learning curve.
As I recall, we still had downrig on the elevator and the impact with a backwards prop. Or I did. I don't. Paul, did you ever use a backwards prop?
Yeah, I used it at the World Champs in 12.
Oh,
That had a backwards prop on it. Yep.
Well, they all have their pluses and minuses, but I've about decided I'm gonna go with the devil I know instead of the one I'm still trying to figure out. Because they both work. They both work, but they'll both bite you. So stick with one and then you don't confuse yourself. And I still fly fuel on a few airplanes. I fly old time and I fly classic, and I'm still flying fuel airplanes, fuel motors in both of those. So we're gonna just stick with one prop and go with that so I don't confuse myself further. But
one of the things I found with electrics that's pretty important are these really light props, these hollow core carbon props that weigh 16 grams. You might as well not have any prop on it. There's hardly any effect from that. And it's amazing.
Yeah.
You can get that same hourglass with that prop that you get with a backwards prop. They're very impressive.
They are.
But
just don't bump them.
They're for electric only, though. But
yeah, no, just don't bump them. I got a buddy down in Charlotte who went through 3 of them in a week, and I thought, oh, $55 a piece. Ouch.
Oh. There's Mike Haberle, who at one contest destroyed 2 of them by, I think, tightening them, and the third one by burning it up.
Wow. I just said, I don't think I can afford this. Yeah. So,
Paul, with the symmetrical airplanes, namely with the inline thrust line and tail and stuff, you tell any difference between forward and backward props, or have you used backward props with that?
I have not used the backwards prop since late 12. I switched to those 11-inch Igor props, and I haven't used one since.
Yeah,
I haven't seen the need for it.
Yeah.
The ones that I liked was that 11. Let's see, what was it? 13 4.5 APC electric pusher prop, but that buzzed so bad.
Oh yeah,
you hit a hard corner and buzz, buzz, and every time you buzz, buzz, you can hear, oh, there go my bearings. The bearings are getting beat up every time it buzzes. I could just see the bearings.
Well, there's that, and if you're in the wind, judges will hear the time difference between buzzes.
Yeah.
And they will think that your maneuver is the wrong shape.
Yeah.
Yeah, there is that.
Hey, if we can, if I can try to get everyone to unmute themselves so we can give Howard Rush a round of applause and appreciation. Give me a second.
And now.
Let me see here. And Gary Sinclair, if unmute yourself, and Tryon, unmute yourself. And Stephen McMalley, unmute yourself.
Well,
and John Miller, unmute yourself. Mike,
thank you.
Thank you. And yeah, let him know how much.
Here, well done.
Thank you very much, John.
Well done.
Thank you. Thank you,
Howard. Thank you.
Amazing.
Thank you very much. Appreciate it. Thank you. Excellent. And you know what? The time is out. We're going to be ending the live stream portion of the show, but we're going to continue on in the after party. So you don't have to go unless you have to go. But we're going to turn off the live stream. It won't be streaming on YouTube anymore. And then you can really tell Howard what you think about his presentation. And so anyways, I want to thank everybody for coming in. And this is Friday. Hopefully you have a chance to do some building in your shop or organize your shop or do some flying back and tell us all about it Monday. So until then, fair winds and tight lines.